Hello and welcome to the 12th lecture of our syllabus and the 5th lecture of the topic IC voltage regulator. In the last lecture we studied about 3 terminal adjustable voltage regulators. At a look of the syllabus, when you look at the syllabus, this many topics we have finished. These remaining 4 topics will be finishing in today's lecture. So in today's lectures we will be studying about 4 terminal voltage regulators, and in 4 terminal voltage regulators we shall study 4 terminal positive voltage regulators and 4 terminal negative voltage regulators. Then we shall study dual voltage regulators, that is voltage regulators which give us 2 different voltages, and in that we shall study non-tracking voltage regulators and tracking voltage regulators. So let us begin with 4 terminal positive regulator. As the name itself suggests, a 4 terminal positive regulator will have 4 pins. One is the input, another is the common ground, then you have the control pin which controls the amount of output current voltage, and you have the output pin. So this makes it 4 terminal regulator. Previously we had 3 terminals, input, output and ground. Now we have the 4th terminal also, input, output, ground and the control pin. So MuA78G is one such commercially available voltage regulator. So in this regulator the control is achieved by varying this feedback network, the voltage at this feedback network. So normally the voltage at this control pin is 5 volt. This is a basic circuit shown here. In the case of a 3 terminal regulator, we varied the output voltage by varying the pedestal voltage at the common point. Pedestal is a voltage which is raised up above the ground. But here we will not do that. We will be varying the feedback network R1 by R2. R1, R2, and the output voltage here is given by this formula. Vout is equal to 1 plus ratio of R1, R2 into your control voltage, where your control voltage is 5 volt for MU78G and MuA78MG series. The current which should pass through R2 is recommended to be 1 milliampere. The minimum output voltage that you can get here is equal to your control voltage, which is normally 5 volts, and by varying the ratio of R1, R2 you can increase the output voltage up to 30 volts. Along with increasing the output voltage, you can also increase the output current capacity by introducing a bootstrap emitter follower at the output as shown in this figure. Now the output of the IC is given to the base of the transistor. So as the output increases, the base emitter voltage here increases, due to which this transistor will conduct more. And this is selected in such a way that it does not affect the temperature coefficient of the output voltage. Now this transistor Q1 is protected against short circuit by transistor Q2. So in case if there is a short circuit, this transistor Q2 will start conducting and it will drive away the base current of this transistor Q1, thus protecting the transistor Q1. How does Q2 know that a short circuit has occurred? As you can see that the short circuit resistor RSC is connected across the base emitter of this Q2 transistor. So in the short circuit condition, excessive current will flow through this resistor RSC, due to which more voltage will be developed across the base emitter, due to which this transistor Q2 will start conducting and drive away the current from the base of Q1, thus stopping the short circuit and protecting Q1 from damage. In a short circuit condition, this voltage drop across this would increase the VBE voltage of this transistor Q2. Now suppose you have a requirement where you want the output voltage to be less than the minimum output voltage provided by the regulator IC. For example, the regulator IC gives a minimum output of 5 volts and you require 3 volts for your application. So what you do? You add an additional 3-terminal negative regulator so that the output that you get is the sum of the output of the positive regulator and the negative regulator. So in case of our example, the sum of the output regulator will be 5 volt, output of your negative regulator will be minus 2 volt. So finally you will get an output voltage of plus 3 volt. This is the circuit arrangement. Here you have your 4-terminal regulator IC and here you have your negative regulator IC, and the output you get the sum of both their outputs. So the output here is given as V out is equal to V control 1 plus R1 by R2. This much part is the output of this one minus V. V is the output of the 3-terminal negative voltage regulator. So if you make R1 0, then the output will also become 0 because V control will be equal to V volt. Now 4-terminal negative regulator. This 4-terminal negative regulator is just the complementary of the 4-terminal positive voltage regulator. So A79G and A79MG are examples of 4-terminal negative voltage regulator. This circuit shows a high current negative regulator using these ICs. So in this case you can see that transistor Q1 is connected to boost the current, and in this negative voltage regulator the control terminal here will have minus 2.23 volts, and this output voltage is given by V out is equal to control voltage into 1 plus R2 by R3. This is R2, this is by R3. Now the output current capacity is increased by using the external transistor Q1, and this transistor Q1 is protected by the short circuit transistor Q2. Obviously the rating of this transistor should be such that it is able to handle the short circuit current. So as your input increases, input voltage, input current increases, there is a voltage drop across R1, and R1 as you can see is connected across the base emitter of Q1, due to which this transistor Q1 will start conducting, and thus there will be an increase in current, output current. In the case of short circuit, you can see that the current across RSC will increase, and just as in the case of the positive regulator, here also this voltage drop, when it becomes more than the VBE of this transistor Q2 will start conducting and drive away the base current of Q1, thus protecting Q1 in the case of a short circuit. Now how do you calculate the value of RSC and R1? Using Ohm's law, RSC is equal to the voltage VBE divided by the short circuit current, and R1 is equal to VBE of Q1. RSC is the VBE of Q2 and R1 it is VBE of Q1, and divided by the current that flows through the regulator. And this equation can be written as this equation in terms of the gain of the transistor and the base emitter voltage. And here this HFE is the gain, which is which is more than or equal to the ratio of the output by the regulated current. Now we come to the topic of dual voltage regulators. Dual voltage regulators are the regulators which give more than one or which give two output voltages and which are used in many applications. Normally the output voltages are of opposite polarities. but they could be of equal magnitudes also, like 10 volts, plus 10 volts and plus 15 volts. We shall study here dual non-tracking voltage regulator and dual tracking voltage regulator. Let us take the case of dual non-tracking voltage regulator. Now, the simplest non-tracking regulator requires a positive and a negative or non-regulated power supply, and one 3-terminal positive regulator and a 3-terminal negative regulator, or it could use even 2 3-terminal positive regulators. When we speak of unregulated DC supply, that supply can be obtained by connecting two transformers in such a way that one transformer will have a center tip and which is connected to the full wave rectifier here, or you have a transformer which has 2 secondaries and which is connected to 2 bridge rectifiers, or you could take a transformer with a single secondary and is connected to a simple bridge rectifier circuit here. Now in this circuit, the transformer is a simple transformer, but the load should be such that the load at the positive end should be less than that of the load at the negative end, because all the current provided by the positive regulator must flow through the load resistor connected to the negative regulator. Now these diodes are not necessary if you are connecting your load across ground and the regulator. Otherwise, if the load is connected between the two ends of the regulator, then a latch up could occur at the startup. And this is especially true when if one input voltage rises faster than the second one. So these diodes will ensure the proper startup of the regulator by preventing any parasitic action when the power supply is turned on. And the rating of this diode should be at least half that of the load current. Now let us come to the dual tracking voltage regulator. So dual tracking voltage regulator may provide 2 positive or negative regulated outputs, or a balanced or unbalanced positive negative output. And a single external adjustment can be used to change both the outputs simultaneously. So you could use 2 3-terminal or 4-terminal regulators to form a tracking regulator. You get tracking regulators available in one single chip, that is monolithic IC, and LM125, LM126, LM127 are examples of such a dual tracking voltage regulators. So this figure shows a fixed dual tracking regulator which is made using 2 3-terminal positive and 3-terminal negative voltage regulator. Here the operation amplifier op-amp is used as a comparator. Resistor R1 and R2 are matched resistors. And how is tracking accomplished? The output of this op-amp is connected to the common terminal, that is to the ground terminal of both the ICs. So as a result, the difference in the output voltage will be reflected in this ground terminal. So the positive output and the negative output are both compared to this common point. So if there is any change in the output of any one of the regulators, an opposite change takes place on the common terminal, this here, and which also affects the change at the other regulator's output. So if the output of the positive regulator decreases, the negative regulator will also decrease. And each regulator will have its own reference here. So no slaving would occur, that is, each one would be independent. The increase of positive would cause an increase in negative, vice versa, the increase in negative would cause an increase in positive. And the degree to which this tracking is maintained depends on the matching of the resistors R1 and R2. Because the magnitude of the positive, because of the ratio of the magnitude of the positive output was upon the negative output is equal to the ratio of this 2 resistors. The same circuit could be used for 2 non-symmetrical output. The output need not be of the same value. We have to take care that the supply of the op-amp does not exceed the maximum allowable value. Thank you.